OH. Hey, thanks for that. Thanks for that heap. Um, so yeah, like I said, our theme for today has been more about the diffuse interstellar medium, diffuse OH. Um, we've had a few talks already. This morning, my time, probably before some of you woke up. The recordings of all of the previous sessions will be put up onto the website as soon as we can manage to be organized enough to get that up. It'll be throughout the workshop. You won't have to wait until the end. And I'm also going to get all the speakers to share their slides with me, and we'll put those up as well. So just before we dive into our very interesting talk today, I was hoping that we could share a couple of our introductory slides that people have been so kind as to share. So I hope you're prepared because I'm going to pounce on people who've just arrived. So let me share my screen real quick. And the first person that I spotted was Michael. Would you be able to introduce yourself if you're still there?
Yes, I'm still there. Hi. Yeah,
Hello.
hi. I'm Michael Rugel. I'm a Johnson Fellow here at NRAO in Socorro, New Mexico. I work mainly on different aspects of the evolution and structure of the interstellar medium, mainly with galactic plane surveys of the OH 18 centimeter lines. That's been in the northern hemisphere, but also some extensions towards the galactic center and the southern hemisphere with Meerkat. And yeah, I'm gonna present tomorrow some results we got also related to OH absorption in more diffuse regions of the ISM and their abundance. And yeah, I'm very excited about learning of all the the super interesting science which is uh, announced in the program, and I'm also very curious about what we can do with next generation telescopes.
Thanks for that, Michael. Okay, next person that I noticed was Ningyu.
Hi, hi everyone. I'm Yin Yu Tang from Anhui Normal University, China. My research is the evolution of interstellar medium in the Milky Way. So the OH study is just one part of my study. So we have finished some studies towards OH. The first is to detect the CO dark gas with OH absorption toward background continuous source, and another is OH3 towards the molecular crowns. So that's all. Thank you.
Thank you for that. And one last person that I noticed, Wenjin.
Okay. Hello, everyone. I'm Wenjin Yang, a postdoc at Nanjing University. My research focuses on various major species throughout the ISM cycle. I'm very glad to join this workshop and look forward to having a comprehensive view of OH molecule and of course with its major emission. Thank you.
Thank you so much for that. Okay, so let me stop sharing there. So if I could direct everyone's well, I don't know if attention, if you want to split your attention, but if you haven't already hopped on to the Slack session for this one, because we're going to have this talk is also going to be shown again in one of the delayed sessions. So there's going to be a lot of ongoing conversations with people on the Slack. So if you haven't already joined the Slack, please do that. The links are all on the website. But you might have to add yourself into the individual channels. We have channels for each of the sessions that we have for the workshop. All right, so let's hear from Serge.
So I should start the talk, right?
Yeah, go for it.
Should I start? Okay. Okay, let me share the screen. And can you see the slides? Okay. So I'm Sergei Balashev from Ioffe Institute from St. Petersburg. And what I want to talk, actually, I'm not an expert in radio observations in OH. And most of my time I was study molecular hydrogen absorption in optics. I will talk about this. And I want to make a bridge, maybe important bridge from this optical side observations to the radio side. Because in my opinion that what we will talk about OH in diffuse ASM and H2 that we observe in the optical ultraviolet, depends on the redshift, it's more or less the same gas. So it was interesting maybe that we can share some interesting idea. But yes, we started to work. I also started to work on OH at some point, and it was this work was done mostly with Neeraj Gupta and PhD student in our universities, Darya Kosenko. And then where I applied this formalism to one observation, and now we also prepare with Neeraj Gupta some observation with mouse. About OH, and I think Neeraj will talk about this tomorrow. Okay, so I start with, I don't need to start with maybe introduction because everybody knows this about OH molecules. It's a special workshop, and there is a lot of observations in emission and the measures of OH and OH emission, but also what we will want to talk about is the diffuse gas. And when it's diffuse gas, it's very hard to detect in emission, and it's much easier to detect in absorption toward the bright sources, background sources, radio sources. And this was done in recently, maybe in many, not many, but some studies. Please don't throw in me stones because I maybe not cite all this works, but just highlight some of them. Maybe I will be happy if you share with me more relevant data. And this is typically what people observe. They measure the OH column densities worked by Anita and also by Michael, and I think he will go to speak about tomorrow of these observations. And also versus, for example, NH1 column density, which also measured in 21 centimeter absorption. And what is interesting here that when we see these gas, this is the data from another observations shown here in the on this in this panel. Then we know that this gas is already correspond to the molecular bearing gas, because in atomic gas you expect that the OH ratio should be something 10 to the minus 10. While in the molecular H2 bearing gas, it's can be up to 10 to the 7, 10 to the minus 7, 10 to the minus 6. And as you see here, this is the ratio is more or less 10 to the minus 7. Here it's H1 column density, but H2 column density typically is more or less the same order of magnitude when you see these side lines. So basically, you can just use it like the ratio of total NH and just divide the column densities. And that means that these identified column densities correspond to the diffuse molecular interstellar medium. And also there was some searches of OH in the extragalactic absorptions, and it was done several years ago by Neeraj Gupta. This is a figure from his work of 2018, and the detection was slightly higher column densities, and mostly this is because these gravitational lens systems, when you see the specially preselected to absorption, but this is another story. Maybe Neeraj will talk about this. And more surveys are going in the future with Meerkat, with SCAP, maybe other telescopes. And one of the scientific tasks is a blind surveys of OH absorption. And when you talk about the blind surveys, when you don't know when you observe, you not observe from the galaxy. When you see the also sight lines is cross through the galaxies, then in any actual absorption survey, but in this blind survey, the detection rate is proportional to the cross section of the gas. So the more cross section you have, the more detection rate you will have. And that is why actually when you make the blind surveys, then your absorption will be dominated by diffuse gas, which have much more cross section because it's not so dense like dense gas that you absorb in emission. And basically what we are going to observe, we already will make some observation with mouse and try to start to analyze it. And Niraj again will talk about this. We are talking about diffuse gas, molecular gas. And in this sense, actually, we also have observation from the actually quasar spectroscopy. People usually say that it's not impossible to measure H2 directly in emission, but this is not true. I mean, H2 can be well studied with electronic transition between the ground state, electronic state, and excited state. And this is so-called Lyman environment bands. But the problem in our local galaxy is that this absorption located in the UV region. So we can observe only with a telescope, even not with HST, only with space telescope like FUSE. FUSE made a lot of observation of H2 toward bright stars in our galaxy and partly in the Magellanic Clouds. But what's interesting that we also can study this gas using at the high redshift, because when you have a redshift, your this electronic transition, which actually started from about 1000 angstrom, they are shifted to the optical wave band. And if you have absorption systems with a redshift more than 2.5, then can see this gas H2 absorption directly in the optical spectrum. You can obtain the optical spectrum of usually quasar is used for this as a background source with a very high signal to noise, relatively high signal to noise, and high resolution. That is why it's a bit paradoxically, but molecular hydrogen is better in absorption, better study in the high redshift than in local universe, because we can obtain sometimes even very high resolution spectrum for these sources. And typically we see another important thing that along with H2 absorption, we also see a lot of, since this is UV transition, this is very rich region of transition of waveband, when there is a lot of transition from metal lines, sometimes from CO molecules that directly in absorption, we see HD molecules and so on, and other tracers of the cold gas, like chlorine. We can study in detail these systems. And this is typically what we now maybe you can say routinely do with molecular hydrogen and optical bands. So usually we preselect the sources using some shallow spectroscopic surveys like SDSS, and this is spectral resolution of 2000. And then we are going to VLT typically because it's available to apply for this telescope in a study with higher resolution, for example, shooter or UVS with 50,000 resolution, spectral resolution, study this absorption. And this absorption actually very rich information, contains very rich information because there is a lot of absorption. It's not like one line, it's a lot of lines, like 100 lines of H2. And they are correspond. This is black here on the panel is absorption spectrum, and red in the model of the absorption profile. And we see many transition from different rotational levels of H2, and can model all together with to obtain quite well constrained on the column densities and made like different analysis. For example, the interesting thing here that if we measure the lines from different rotation levels, we can constrain the column density on each levels. And here at the top left corner, you can see the top right, sorry, corner. You can see the population diagram of H2 that we observed. It's a black point. And then these actually levels in H2, they are typically in the condition of cold DSM is populated by the collisions and the UV pumping. And that means that by modeling of this population, we can constrain both the number density of the medium and UV field. And we made some serious work with mostly Daria Kosenko on this topic to study the physical conditions, and also my collaborator Pascal Notre Dame to study physical conditions on kinetic temperature also can be constrained by orthopolarration, number density, thermal pressure, UV field, and also with some abundances of element, we also may constrain cosmic ray ionization rate in the medium. So actually H2 and associated species provide very rich information about this diffuse gas. So this is my point, I would say. And the statistics now that we have. So now we have about 50 absorption system, well studied in details, starting from like how much? 40 years ago. And plus 20 new now we also analyze, and Daria, I think, will publish at some point this new system. So we have about 100 of systems of H2 absorption already studied at high redshift. I will talk about high redshift using, so it's redshift more than 2. And also we have some candidates from SDSS. There will be more candidates from DAISYs, for MOST, and so on. So we know how to preselect these systems. We know how to absorb them. So and we have some information. But what is interesting that this now I go into OH, try to make the bridge to OH, that at some point we made the stack analysis of DLAs. This is typically absorption systems of neutral hydrogen, large neutral hydrogen absorption systems, and absorb also in quasar spectrum. In some of DLAs, like 5%, we can find H2, molecular hydrogen. And at some point, there was a stack absorption of DLAs was made, and with Pascal Notre Dame found H2 absorption lines here. And from this measurement, we was able to measure the column density distribution of H2. Because like 15 absorption system, maybe it's not enough, and also they are not very well like selected, not blindly selected. Sometimes it's not blind selection, so it's hard to guess the column density distribution. But from this stack observation, we was able to constrain the column density distribution of H2, and we find this is a red line here, and this is the number of system detected at some column densities and at some absorption distance. In fact, this quantity just provide you the cross section of the absorbing gas that you have at some particular column densities. Or you can calculate the identification rate in the surveys using the integration of this quantity. And we found this is a red line here in the graph that in this plot that this is very it's agree with local measurements, which actually was a bit surprise for us, but still at local measurement from the emission of dense gas. And we have some kind of continuous distribution, but we expect that the normalization of this quantity should change, but this is another story. And the question was at some point that if I can constrain the dependence of an OH versus the column density of OH versus column density of H2, how it's depend. Then using this measurement of the column density distribution of H2 gas, we can estimate how what we expect for the column density distribution of OH gas, and then we can say how much of absorption we will have in these blind surveys of OH, or what we can say from this absorption. So for this, yes, for this you need to chemical modeling of OH. There was a lot of like works back to the 70s that study OH chemistry in the diffuse gas, and some of the reference is provided here. And the main idea was that the OH is directly the rate of the abundance of OH is very effectively. OH is very effectively produced in the presence of H2, so abundance go up when you have H2, and there is some channels already discuss how to use this, and you hear everything here is H2 is involved. Yes, and so this is a graph of the sum of calculations, and you see once H2 is going up, abundance in the medium, then OH is also raised up. So, and it's going up to the 10 to the 7. It's typical ratio that's observed in the diffuse medium. So we also developed our own chemistry model to calculate OH abundance. It's a bit different visualization of this chemical network. And the idea was the simple that we will use for H1, H2 transition, which actually important ingredient in the cold medium, because OH production depends on H2 abundance. We use analytical description by Stenberg 2014, which actually just analytical description. So you don't need to solve any radiative transfer and so on. And it's very easy and very fast. And then we also solve some balance equation for the ionization, hydrogen ionization in the medium. This is actually the only equation that we have to solve in our model, because our other abundances is just can be written analytically and including the OH oxygen network to produce OH at the and here I show you the compare the example of our calculation. We compare with some sophisticated code like PDR Midon, different abundance with colors shown here in the plot as a function of H2 column density. And you see our calculations so well agree with PDR Midon, but PDR Midon is typically calculated a few hours, and our code just calculated in like I don't know, a few seconds. You need to calculate all the model to produce OH abundance. And yes, our model certainly is applicable only in some region correspond to diffuse gas, when carbon plus is the main constituent. So we don't consider CO at all production, and we also can be applied to the diffuse gas. And here is also what is important, that we can study how the OH abundance versus, for example, H2 column density or NH column density depends on the physical conditions, because actually it's certainly should depends on the physical conditions. And here how this relative abundance of OH changes with metallicity changes. It was interesting to study because at high redshift we see typically lower metallicity systems in our Milky Way galaxy. How it depends on the cosmic ray ionization rates. Next, it's on the density and UV field as well. And again, here the calculation with Medon and our code. So basically, we have very well agreement between this, so we can trust our calculation, I would say. And here again, one of the first results that I can show that here, for example, how we can reproduce the observations of galactic. This is from work 2021, and I use the data from survey of Lee 2018. And this is black point is observed for 1, and the curve here is just when we calculate our model, depending on the changes, the cosmic ionization rate, changes the number density and UV field. And you see that you can find in some reasonable values, you can find description of most of the observations here. So basically, you can, in principle, study the physical conditions based on the observations and the modeling. Some constraints to make. You can make some constraints, and this also done with. This was work by Minter and Felix Lokman, and they just contacted me because they have observations of Smith cloud, which is a high velocity cloud, not in our galaxy connected, and they have actually upper limit on OH column density. But from this upper limit and the measured H1 column density, we was able to constrain, for example, the number density in this cloud to show that this cloud is not represented the cold medium. Otherwise, you will have to see some more column density than we have upper limit, and also some constraints we was able to get from for H2. And the basic idea that because we can since the model is very quickly calculated, this model of diffuse OH, you can very efficiently sample the models and, for example, use the Bayesian approach to get this constraint, because you can efficiently calculate a lot of models and using this. And the last one that I want to talk about is idea to how go back to the H2 connection and column density distribution. Now we can, for example, connect to calculate column density distribution of OH based on the H2 observations. And for this, we need just to use dependence of NOH versus NH2. Here, the calculation depending, again, it also depends on some physical conditions. And in principle, in blind surveys, we selected different galaxies, so we can expect some distribution of these parameters, and they will affect the ratio, so we need to take into account. And we just made this simple integration over the different spread of the physical conditions using this calculated function, and using the observations of gamma function for H2 column density distribution. So we assume some reasonable ranges for the UV, cosmic ray, metallicity, and number density, and ended with this column density distribution of OH. This is kind of predicted column density distribution from H2, from the side of observed with H2. And the idea is that at the end, we get some values. Let me just remove this. Okay. Here, this is that it shows the detection rate that you observe, that you expect the number, basically the number of absorption with the column density is higher at some level. So if you have, like in your survey, for example, sensitivity level of 10 to the 13, so you expect that you will obtain one OH absorption system in delta X, which is absorption distance of about 1000. So if you compare with the current survey that probably will already done, or maybe it's in an ongoing survey. So we expect actually here the redshift part, but it's more or less for the low redshift is close to the absorption distance. So you not expect them to be a lot of OH column density, OH systems to detect in these surveys actually. So it's not so, I would say, okay. So my conclusions are a bit out of time, but sorry for this. So what I want to talk, that I show that we have some model, a simplistic model to calculate OH abundance in diffuse medium, and we can study how this abundance depends on the physical conditions in the cold medium. It's a UV field, cosmic ionization rate, metallicity, and number density. And what I also want to stress, more than the OH absorption in the radio that we typically see in these blind kind of absorption studies, it's the same that we see in optics, high column density systems that we see in optics. And there is pro and cons for this. For OH typically is not color biased, so there is no dust obscuration. Is not important for this. While for H2 it's very important. Some sidelines has dust obscure, so we cannot study this. But H2 provides, if you study H2 in ultraviolet, you can get much rich information about absorption medium, and you can study some of the physical conditions like just using H2 and also additional species. So it's really provide a lot of information. Okay, and also I show how we can calculate the column density distribution and prediction for the blind surveys. So I see in some future we can use the observe OH abundance to, for example, constrain some physical parameters evolution of the diffuse gas in using this prescription. Thank you very much. I can stop here.
Thank you very much for that. That was super interesting. It's an interesting topic. It's new to me. So thank you very much for that. Do we have any questions? Looks like he.
Oh, thank you so much for a very, very nice talk, and very, everything is new to me here, mostly. But I'm happy that my plot, you can see the upper panel is I plotted that, and
Okay.
with the data, and with the upper limit as well. Yes. So how did you get that kind of data from the paper?
What do you mean? I just don't.
So I think,
You
yeah, I
mean
know that's the data
just
for that plot.
Yeah, so I don't remember exactly because it's like 5 years ago, but
Yeah.
just took the data. I don't know, maybe digitalize it. I don't remember.
Oh, really? Yeah, I think a Dili or Ningyu would provide one as well.
Or maybe I provide. I don't remember actually. Sorry. I need to take a look to go back to the it's already 5 years
Yes,
ago.
that's very nice. Of course, I didn't know that our data there can be very
No,
useful
it
for you.
was. I think it was from I think maybe Neeraj give me yes, I think Neeraj is not here. I think since he has he used, yes, maybe I start to remember. So basically I think here this is extragalactic observations work by Neeraj, and I think I used just this from his he provided me, so maybe he is better to answer this.
Well, yeah, but thanks for that. But my question is that you talk about your simple model, but I don't think that's quite kind of I mean, it's not really simple to me. Can you explain a little bit about that, your model, and then how did you get the a few physical parameters like the column density, number density, and then something, yeah, at the end of the conclusion slide. Can you go back to that?
Yeah. So about the model. So basically, maybe I have additional slides. Maybe it's better to show. So model actually is look like here. So you have the plane parallel geometry of the gas or slab of the gas, and UV field is follows one of sides, and it's formed the H1 H2 transition. It's from Stenberg. There is description from Stenberg of H1 H2 transition here. And you can just calculate the dependence of, for example, quantities as a number density versus NH2 column density, because the self-sheet of H2 is take place in the lines. So basically, NH2 is reasonable scale for this. And then, so basically, this is NH1 H2 transition based on Stenberg idea, and the axis here is NH2 column density of the gas that of this slab that have, okay, again, the UV field that's fine follow on one side of the cloud, and there is some metallicity of this medium, number density, temperature, and we typically assume the column density, the CNM, but we can also calculate now the thermal balance in this medium, but typically it doesn't change too much. So some temperature will be in between around these values. Yes, so then when we calculate this H1, H2 transition abundance, then we can solve the ionization of the gas just basically on in H1, H2 profiles in the medium. And then to solve any like step by step of H plus abundances, H2 plus, H3 plus abundances, and so on. So basically this, for most of the parts, actually, once you have H1, H2, and H plus, then you just calculate analytically. This is very simple. That is why I call it simplistic, because you don't need to solve the whole chemistry net, basically for H2 plus, H2 3 plus, and OH species. Mostly you just can write some analytical expressions. I think it was in our paper 2021, it was already, I mean, written. So yes, and at the end, you just have this like abundance profile versus H2 column density. And then to derive column densities, you can just integrate till some of these quantities integrate over the sideline, and then just get, so, or sometimes you can like double your cloud to simulate that this is cloud that is illuminated from both sides of the medium, but this is small tricks. It's not complicated. Yeah.
Yes,
Yes. So
great.
yes, and then another story is how to go from H2 column density distribution to, where is it? To OH column density distribution. And so here just the idea is we know how much H2 depending on the the cross section of this gas, and we can, like, for example, use H2 column density to predict how much of OH column density in this gas. And this will give you the OH column density distribution basically. But so also, as I said, the model is dependent on what the physical conditions you have. So you need to also like average of the over the physical condition distribution of the physical conditions, because in, for example, in extragalactic blind surveys, you might expect that the physical condition will be different for each galaxy or sideline. So basically, this kind of provide you some dispersion. So yes. Was it understandable?
Yes, thanks for that. I think I generally I understand. Thanks for that.
Harley?
We cannot hear
Hi,
you.
sorry.
Nice talking.
Thanks for the talk. That was really interesting. I had some questions about the model as well.
Mhm.
So my first question is, you say it's applicable to like the diffuse ISM. Do you kind of, it looked like you were defining that by the column of H2. Is that correct?
Well, it's not exactly. It depends. This like where to show you. Yes, this is this shadow stripe is actually, it's just made by hand because it depends on the physical condition. Each model will have different physical parameters, and the basic idea is when you have that this model is applicable only when the carbon is in ionized phase, because when the carbon is not in ionized phase, the ionization rate different, ionization of hydrogen is different because electron is not supplied by the carbon plus. started the thermal balance different because once your CO appears and the temperature goes down. So many things change. And you see here, for example, oh, sorry, I cannot, let me just remove this. You see here, for example, the dash line here, it's a PDRMI dome, right, model. When we calculate at the same physical condition that our model, and solid lines here is our calculation. So we see here in this region, the abundance of different species sometimes raise up, and this is just because CO is going, C plus and C1 and CO appear.
Sure.
Here, and everything is going up. So basically our calculation is not well applicable in this, I would say,
Sure.
because we need to calculate CO in this case, because also CO involved in the oxygen, take some oxygen and so on. So it's a lot of, that's why we are safe in the diffuse gas, I would say.
So that zone is going to vary depending on, say, your radiation field strength, your ionization rate.
Yeah, on the metallicity as well, because
And the
CO is
metallicity,
shielded by the dust. So depending on the metallicity, for example, in H2, we have observation of very low metallicity clouds when we, for like 10 to the 21 point something, don't see any CO at all. So it's will be very dependent on the physical condition, this exact range.
Yeah, okay. Okay, great. Another question I had, okay, so the model obviously depends on metallicity, and I guess you're really dependent on the gas being in chemical equilibrium. Is that correct?
Yeah.
Yeah.
It's a chemical equilibrium model, certainly, because it's a zero solution. You have to assume
Yeah,
some.
okay. There was one thing I saw. I think you were showing, I don't know if they were in the additional slides you just showed, but there was an example of a setup you had where I think I saw you had the radiation field set to 3. Is that correct, or did I missee that?
3. You mean here? It's not a radiation; it's a cosmic ionization rate in
Oh, the
the.
ionization rate. Yeah, okay.
It's in the units of 10 to the minus 17 of
10 to the, okay.
second per second. So this is
Yep.
UV is here. UV radiation field is here. So it's the base model was with standard Matisse field, and we just have higher and lower level.
Okay. I was just a bit confused, but I was like, that seems like a really
Sorry.
strong but yep.
Yeah, I think I was a bit fast, but
No, you're fine. Thank you.
Yeah, I think that.
That's all right. Heap, were you going to say something?
Oh, sorry. Yeah, I just want to say that. How about the size of the slabs you're working here? I think Carly is simulating a few clouds. I don't remember your cloud sizes, Carly, but I think that you include both CO and OH in your clouds.
Yeah, my clouds are a few tens of parsecs.
Yeah, so the size here, you mean the physical size, or because when I talk about the sizes, I typically used to talk about the observation quantities like H2 column density. But typically the total column density of the clouds will be more or less like twice of this, roughly, right? So if you stop at some like 10 to the 20 of H2 column density, then you will have roughly, very roughly, like twice size because of H1 as well, called H1 in the envelope, typically with transition, maybe sometimes more. And so you end, depending on the number density, you will end in different sizes here, for example, in calculation. So it's the physical size for me, like it's not was very important because it's not observable quantities. We observe column density of H2, so it's better to use the coordinate, or I don't know, the physical coordinate. You can say not physical, but to calculate profile, some quantities like H2 column density or an H1 column density, depends if you want to compare with what observation. So basically, this was. So you can stop at any column density. So you just stop your calculations.
Michael, you had a question?
Yeah, thanks so much for the talk. That was very interesting. I had two questions. So one was on the plot of the source of the detection statistics, the overall.
You mean?
Yes, this one. So is that for is a specific redshift range, or that's all at z equals 3? Okay. No,
Yeah, it's for z equals 3 because we have column density distribution of the redshift 3. Yes, thank you, Michael, for this, because maybe I need to explain this a bit. So H2 column density distribution is based on the stack measurement in the SDSS, which have median redshift 3. So we have constraint for H2 and median redshift 3. If you at higher redshift have higher, you can say, normalization of this column density distribution, because, for example, we know that there is a lot of more gas, more molecular gas, for example, at redshift 1. Then your diffuse gas probably also will go up, right? So that is why this plot is shown for redshift 3. But as I also show that from our stack measurement, we find that our column density distribution also agree with the local measurement. So we don't know what in between, and the model know in models, you know that there is a, I think I have also a slide here, that there is a changes of molecular gas, right? So over the redshift. So at some redshift, you expect a few times more molecular gas. This is based on the dense gas measurement in the mission, so it's a bit different. It's not diffuse gas, but if you think that the diffuse gas is connected to this dense gas, then you can expect that the diffuse gas will be maybe also more. It will be more diffuse gas in the redshift in between our local universe and the redshift, roughly 3. So yes, so this is to explain a bit.
Okay. Okay, thank you. So the other question I had was like maybe a bit off topic, but so OH has also some optical absorption lines, right? It has some optical electronic transitions. So
Yes.
and I saw you work on CO absorption. Is there any way to do a direct comparison with the H2 absorption you see in the optical and the OH?
Well, in optical, we search for this OH absorption or H2O absorption for many years, right? And it never been detected. And the reason I think for this mostly is because to have OH, you need the higher metallicity and higher column density, right? Because OH depends on the metallicity basically, and also on the column density. And when you go to the higher column density, you have the dust, which actually obscure in optics and this is like trade-off. So at the column density is very high, you cannot see, and you see not very well your background source, the optical spectrum, because it's obscured of associated dust in optics.
Okay.
So this is the problematic in this case, in this sense. And in this sense, radio observations is very nice because it doesn't sensitive to the dust obscuration. So it was for a long time the problem for optical observations of H2, this gas diffuse.
Yeah.
So
Cool.
we
Thank
do at high redshift not yet did not find any of these sources or not sources absorption of OH.
Okay, cool. Thank you.
Yeah, I had a bit of a question there. Yeah, because I've looked into this a little bit when and I noticed that you showed a plot of mine from one of my papers. So thank you. That feels like I'm slightly famous. I remember having a look at the OH column densities that we were measuring. This was in a survey with Arecibo, and and the kind of that you know that Kingfisher plot that it was this one. And that the sort of turnover point where you would start to see where you would see the H1 to H2 transition was at much lower column densities than we were able to probe with our observations. I think I did a little calculation that you'd have to do like 100 hours or something to be able to see it. So I'm wondering if you've made any predictions of the types of observations that we would actually have to do to detect any of this the OH that you're expecting around this at these low column densities, and especially at a higher redshift.
Well, I think this is already, as far as I understand, this like topics that your observations, I think, already very more or less close to the when the H1 H2 transitions occur. Because, for example, if I go back, go once again here for the plot, where is it? Here. So this is from another survey, right? But the column density is more or less the same, 10 to the 13 of OH, and H1 column density is also more or less the same. And along this line here, you see the numbers. Actually, I forgot to say about this. This numbers is H2 column density along this line of calculation, because this is OH versus NH1. So this is a logarithm of H2 column density. And you see here, for this point, which more or less the same that you have in your survey, you already reach like 10 to the 20 column density, 10 to the even 21. 21 is very, very large H2 column density, so you have more H2 than H1 actually. So you already kind of in the transition between H2 and H1. So I don't feel
Yes,
any
I
problem.
think I meant we were kind of approaching it from the other direction, that we were seeing we already have the H2 forming, but then to be able to probe down when to the lower columns of OH where it's starting to convert. I think I was thinking from the other side.
Yeah, so I would say that yes, yeah. Maybe also there already was a question. The question is that maybe if you want to compare with observation, real observation, right? This is a very simplistic model, but then you can expect, and people typically observe this, and there is if you even just look for the H1 H2 transition and apply this prescription to the optical data or UV data in our galaxy, then you cannot see one cloud. You can typically see the concatenation of different clouds. And in this sense, you have this kind of statistics, and you need to be careful with this. This is not probably one cloud. So you typically need to a bit make more complex model when there is many clouds on the line of sight and you integrate everything. So yes, all this that I present is just one cloud, like a slab cloud, and you just calculate the abundances. Yeah, but at least the numbers here we can reproduce with typical condition of ISM, like number density of 50 and UV field standard and the standard cosmic ray ionization rate. We can go through this point. Okay, if I hope
Yeah, that's good.
answered
Thank
the
you.
question.
Do we have any more questions or points of discussion? Hey.
Oh yes. I'm really interested in your results on the high redshift with the molecular H2 gas absorption.
No.
Yes, so in the model, you can estimate the number density and also the radiation field strength of within the absorption line over there about one towards one galaxy that is a ship two or something.
Yeah,
So
we actually, yes, sir.
So how did you
Please
do
go.
that? From
You mean?
the
Yes, so for this, for H2, we just use the population of rotational levels. Because H2 is populated, we can measure the absorption lines from different levels, rotational levels. We can constrain the excitation diagram of in these levels. And also, maybe, is it?
yeah, so
And
the
then, yes.
levels, sorry, I just want to understand the levels, they are in different absorption feature over here.
Yeah, this is different absorption feature, but this is also different several components, velocity components here. But typically this feature, yes, I have no plot for the whole spectrum, but typically maybe here. So typically this kind of this transition from the zero region level of H2, this is from first level, this is from second, and so on. So you can typically observe the like large bands of the transitions with many lines, 10 of lines from each rotational level, and then you can constrain column density very well, I would say. From the modeling here, yes, it's a bit complicated because there is several velocity component here. So this is basically one velocity component, two. It's a bit maybe not complicated absorption system, but in principle, you can constrain the column densities on several rotational levels, and then just use a model for how to excite these levels. And this is basically collision and UV pumping. Then you can constrain the UV field and the number density just from this observation. Also, we have additional species like C1, for example. They also provide some collision constraint on the collision. So yes, so basically you can constrain this just by observing H2. And we have several papers when we publish this already result from the estimation of the physical conditions.
Yeah, well, great. I think it's really very interesting to me. So in this case, you measure the absorption of H2 using optical, isn't it?
Yes.
And which telescope then?
Typically, to measure well the column density, we need to go for the VLT for UVS, for example, or we can use archival data we also use from Keck, from high-res telescope. In some cases, we cannot go to very high resolution because actually typically quasar at high redshift, they're quite dim. So we went for also VLT X-shooter spectrograph here, the spectrum of X-shooter. It's you see that lines is not so resolved. So here this is different one spectrum observed at different resolution basically. So and here the panels is show how well you start to resolve these lines when you observe at high resolution. So I think like 30% of the maybe 40% of the systems out of 50 systems was observed with UVS, and most of other with a shooter to get the column densities.
Great, thanks so much. The last question, please. Can you get the temperature of the gas in this case?
Yeah, temperature, it's typically people say that at least modeling show that in H2, the ortho-para ratio of the H2, in H2 you have ortho microhydrogen and para microhydrogen. But actually not different actually molecules, right? They are not have no like transition in between. So and they convert using the collision with protons, so with H plus. And people typically show that at modeling, at least at high number densities, relatively correspond to the cold neutral medium. They are converted and converted to the temperature of the gas. So basically, this is a well-known thermometer of H for the gas. And basically here it's in this diagram this is J0 level and J1 level. So parallel H2 is like J0, J2, and J4, and ortho is J1, J3. So they basically, yes, this is the ratio. And I have a plot. We also have statistic of this observation, and we see for H2 that all the systems is located around 100 that we observe with H2. All the systems is located with 100 kelvins. There is some dependence of temperature on the column density. So the higher column density of H2 you have, the lower temperature becomes. So there is some trend, but typically this is well measured quantities. Much well measured at the like number density and UV field.
Great, thank you so much.
Do you have any other questions or discussion points? No? Okay. Well, so I know I mentioned at the beginning that we should move everything to Slack, but unfortunately Sergei can't access Slack. So if you do have any
maybe
questions, huh?
Yeah, maybe I will try from my phone or maybe using VPN, but I have no time on the weekend to play with this, so I will maybe try to connect somehow.
No
Not sure that I will be able, but just if you, yes.
Okay, yeah, no worries. I was just going to mention if anybody does have any questions, you can still put it in there, and if Sergey can't access it, I can just send him an email and post his answers in there. So if we can thank Sergey again for the lovely talk and all the discussion that it inspired. Thank you.
Yep. Thank you. If you're interested in for any details or maybe to try to apply this, so just let me know.
Absolutely. Thank you
I'll
very
be
much.
happy to play.
Cool. Okay,
Thank you.
well, we might just end the session there. So thanks again for Sergey, and thank you for everyone who came, and particularly thank you for everyone who had lovely questions. And yeah, we'll see you in the next session.
Bye.
Bye-bye. All right. Thank you for that, Sergey. Hey, thank you for asking so many questions, because I don't know anything about that.
I mean, great talk. I mean, it's really interesting to
See,
me.
it is. Yeah.